All right, so we are done with the technical program, although we are having a historical moment here in MMSys, in my opinion, because this is the first time we are organizing a grand challenge sponsored and organized by Twitch, actually, about low latency, which is one of the hot topics for this year. So to, as the main organizer, I would like to pass the ball to John Bartos from Twitch. He's online. He's joining us live. He will go through the challenge, some details, and then he will share some results, what he has found from the submissions, and then we will all learn the results. So the winners and the runner-up. Okay. Thank you, John, for joining us. It's yours.
Thanks, Ali. Can everyone see my screen?
Yes, we can.
Okay, great. Let me just get situated on my end. Perfect. Cool. So like Ali said, this is Twitch's grand challenge on near-second adaptation algorithms. Before I begin, I just want to say thank you to everyone who participated, especially the 3 teams who submitted really interesting and thoughtful and well put together papers, and especially Ali himself for helping guide us through this process. So this is going to be a pretty high level talk, just going to go through the challenge setup, the results, which nobody knows yet, so it's a little bit of tension there, and then kind of a rationale behind why we chose the winner. So a little bit about us first. We are the video playback team at Twitch. And in the context of this challenge, we use chunk transfer encoding to deliver low latency streams at scale. I'm John Bartos, and I'm a senior engineer on this team. So we put together this challenge because we know how difficult low latency streaming is, especially the adaptation side. We want to draw focus to low latency adaptation algorithms and source ideas from the research and academic community. So on to the challenge itself. So the goal of this challenge was to design an adaptation algorithm which provides a good quality of experience at near second latencies. And a good quality of experience for us, very simply put, is less stalling, better quality. There's way more that goes into that, but those are two good goals to hit. So we added a few constraints and considerations that we feel put this challenge in a new space. And the first is a target latency of 1 second, which is really low for HTTP. And the second is that the player will pre-request segments before they're available, which means that the player will actually, before the current segment finishes downloading, it does the request to the next segment. This is what Twitch does in production. And it reduces, it swallows up the round trip time, which is good, but it reduces burstability, which makes burst-based throughput estimation algorithms a little more challenging or a little less accurate. We also added a few considerations. The player can and will change the playback rate to maintain target latency, and that the authors should not assume that viewers will have good connections. Twitch has a really diverse population of viewers. I'm in New York. We have viewers in India and Brazil and all over the world. Algorithms should be general enough to apply to all of those viewers. So the setup. We created a local end-to-end evaluation framework for our participants, and it has 3 broad pieces: a streaming engine, a network simulator, and a metrics recorder. And we created this because we wanted to make it easy for anybody to participate, and we wanted to make sure that people had a level playing field, and also to help us reproduce results. And we did have a lot of participants, so I think that this did go well. So the streaming engine, it delivers and plays a VOD asset frame by frame using chunk transfer encoding. And we decided to use -JS for this, mainly because the Twitch player is not open source. -JS is familiar to researchers, and it does chunk transfer streaming out of the box. We also use an open source Dash server, which restreams an asset using chunk transfer encoding. which is great. That is courtesy of FF Labs, and the attribution is in the GitHub link. We also use an FFmpeg, and we stream in half-second segment sizes, and we use good old Big Buck Bunny as our test VOD asset. So the network simulator throttles the connection speed according to predefined profiles that we set up. So for this, what we did was a Chrome instance that's controlled by Node.js through Puppeteer. And we used the Chrome DevTools protocol to actually throttle the network conditions using the same tool that, if you're familiar with Chrome, that you can use in the network tab dropdown. And we created 5 different network profiles, which we believe covered a wide range of scenarios. Important to note also here is that the framework is not capturing startup behavior. We actually wait for the player to stabilize, and then we capture metrics. We did this because we don't care as much about startup behavior for the purpose of this challenge, and we want to make sure that the metrics we're gathering actually represent the changes in network profile that we're making. So the stats recorder, simplest part, it's just some JavaScript and HTML, record stats. And in broad, it does aggregates, like it averages bitrate, but it also records per segment metrics that are pretty detailed, and you'll see how we use that later. And the environment, it was all run on my MacBook. 2019 MacBook Pro, Chrome 81. This MacBook is fast enough to run FFmpeg, producing the bitrate ladder for this challenge, in addition to running -JS. So the evaluation itself, how do we do that? So we use the performance stats that we gathered from our evaluation framework, but we also read the papers and we studied them, and we did our best to really understand the ideas, the assumptions, and the potential of each idea. And we did this because we know synthetic benchmarks aren't the same as real world. It's much more complicated. There's no TCP business involved here because it is local. And it doesn't really tell the whole story. So we wanted to make sure that we were giving everyone a fair chance. And so for the objective analysis, we ran each of the 5 network profiles 5 times, and we averaged the following stats: bitrate, stall duration, latency, playback rate, the number of switches, and the buffer occupancy. And using the per segment metrics, we created time series charts for a single run of each profile. So the aggregates gave us, a high level view of what's happening, especially compared against the StockJayS algorithm. But the per segment charts gave us a really good understanding of how the algorithms behaved in response to changing conditions, and the correlation between certain metrics like playback rate and stall duration, which is an interesting one. So subjective analysis, we really just asked ourselves a lot of questions. And for the machine learning papers, we did have the Twitch machine learning team help us understand those ideas too, which is really great to have that resource. So broadly, it boiled down to 2 things. Do we think that this algorithm could perform well on the diverse Twitch network? And what is the potential for each design, and have the authors realize that potential? This challenge, I think it only ran for 3 months. Twitch took way longer than 3 months to build. We know that it's not a lot of time, and we want to make sure that great ideas, which maybe didn't reach their full potential in the submission, were given a good opportunity. So on to the results. Like I said, disclaimer, we're going to stay high level for this presentation. We have the full data sets, which I'm going to share with the authors after this. I can also share the data with anybody who asks, but I have to email it because of the sharing settings on Twitch's Google G Suite. So StockJayS was our benchmark, and we set it to a latency of 1 second. Out of the box, StockJayS will also change the playback rate to maintain that 1 second latency target in a half-step interval either way, so 1.5 times or 0.5 times. And over on that chart on the bottom, we see our 5 profiles. They are pretty long each, pretty high bit rate, and not too much in terms of switches, 5 or 6. And we see that StockJayS doesn't stall that much, maintains a pretty good latency, but it doesn't have really, it doesn't maintain a high bit rate. And looking at the chart, we can see why. On the right there, it's a, just FYI, this is a 2-axis plot. So on the right, you have your access for bit rate, and that goes in the ladder of 1,000, 600, 200. And on the left, you have your playback rate and latency and buffer in terms of milliseconds or thousands. So you can see DashJS right off the bat overreacts to the initial drop in bit rate to 1200 kbps, and it pretty much stays there the entire time. And we could see towards the middle there how the playback rate starts to increase as latency starts to increase. And that's not a great user experience because viewers are hearing music sped up, the voices may sound a little bit squeaky. It's not something that we consider to be good QoE. So L2A LL, and unfortunately we didn't have time for the authors to present their ideas before this, so I'll just do a little blurb about each. L2A LL uses online convex optimization, so kind of like a multi-arm bandit approach to predict what the next quality should be. And it does this primarily by looking at the impact its last decision had on latency. So it's not using throughput to predict the next quality. We really like this one. And we could see that it increased bitrate by about 60%, but stall duration was increased by a large amount, as was latency and the number of switches. And we could see in this chart here that L2A does a really good job out of the gate of not overreacting to the initial drop in bitrate. It stays steady at the highest quality. And it does respond pretty quickly to that initial drop, but it does overreact, and it was not quick enough to actually prevent stalling. And we could see here that at around t equals 30, we see latency increase, and then we see the quality drop. And I think that's the proper way to interpret this chart. When we see that red line increase, the blue line is expected to go down. The authors could correct me if that's not true, but I've been talking with them quite a bit, and I believe I understand their machine learning approach pretty well. We could see one fatal flaw of, well, not fatal, we could see one flaw of L2A here, and then that is the playback rate causing stalling when latency increases and the buffer is low. And we see this starting at around t equals 60. The playback rate goes to the author defined max of 1.3, and it just causes the buffer to bounce off the bottom for almost until 110. So quite a bit of stalling caused by playback rate. The authors did not change the default DashJS behavior other than lowering the latency amount quite a bit. So towards the end, we start to see some positive signs. We see it trying to upswitch at around t equals 80. We see the latency spike downwards. We see it upswitch. However, the algorithm appears to observe that it increased latency and then just switches back down. But upswitch behavior is positive to see because that is a big problem with the default DashJS algorithm. LOL. So LOL, the authors actually submitted 2 different algorithms, a learning rule based on self-organizing maps, and a heuristic rule that uses fast MPC or model predictive control. And we see across the board, bitrate was increased a lot, 150% about. Stall duration was increased by quite a bit too, as was latency. Playback increased quite a bit, and number of switches a little less for learning, but a lot for the heuristic rule. And on the chart, we can really see how well the throughput estimator works for this test. And these are the same authors at Wesleyan University who made ACTE that was announced last year, which is the burst-based throughput estimator, and they did refine it for this paper. And we see these refinements appear to be paying off in these tests. It responds quickly to the first drop in bandwidth, but doesn't overreact. Not quite quick enough to prevent stalling, but we see it track very neatly, for the most part, the changes in bitrate. Still a little bit laggard on the up switches, which is still fundamentally difficult, but it does a pretty good job overall. Again, the authors did not address or did not change StockJayS's default playback rate, and we see those playback rate increases causing stalling when the buffer is low. So this is the heuristic algorithm, FastMPC, and we can see where that switch increase comes from. It flaps a lot when the buffer is low. We see again that the throughput estimator, though, appears to be doing a pretty good job at tracking the actual changes in throughput. So Stallion is, it was a combination of two changes. One, the authors actually addressed the playback rate increases causing further stalls, which we really like to see. And also the authors put a standard deviation filter on the StockJayS throughput estimator in an effort to reduce the amount of jittering. And if you read actually the LOL paper, they graph the StockJayS throughput estimator, and it does jitter a lot. So two big problems that they did aim to address. And for fairness, Stallion was compared against StockJayS at 1.5 seconds of latency because the authors increased Stallion's latency target to 1.5 seconds. And that actually makes a really big difference on the stock algorithm. So we wanted to make sure we were doing a fair comparison there. We see that Stallion increased the bitrate by quite a bit, but also the stall duration and latency and number of switches. However, the percentages of increase look scary, but they're not that big. We could see stall duration was increased by 70%, but that's from 1.6 seconds to maybe like around 3 plus. So not too big of like an actual increase. And we actually thought that this was a pretty favorable trade-off, having a huge increase in bitrate for just a little bit more stall duration. And we could see from the chart here that Stallion does a little bit of a better job of upswitching than StockJayS, but it does suffer from a few of the same problems, which is overreaction out of the gate, and still very long times to upswitch. However, we see that the yellow line playback rate stays pretty steady. We have a few moments where it does increase when the buffer starts to recover over the threshold that the author set, but overall it is not contributing to more stalling, which is a good user experience. So, conclusions. So L2ALL is innovative. When showing this around to machine learning people at Twitch, everyone was like, whoa, this is cool, this is interesting. And the playback team thought the same way. We really liked how the authors framed adaptive streaming as a convex optimization problem. It seems really well suited to streaming. And we also thought that convex optimization is a fast expanding field, and L2A stands to benefit from this research. And we really want to commend the authors here for being very rigorous in the way that they proved out their algorithm and the mathematics and ideas behind it. We thought that was a really great contribution to the ABR research space. So it has two main flaws, which is the playback rate, as you saw, causing more stalls. And then the authors use a default throughput estimator, which is not very accurate. And I know I said before, they don't use it to predict the next quality. However, they do use a throughput estimate as like an oracle to measure the distance between their choice and the ideal choice. And they say that the ideal choice is the one which most closely matches the throughput, very simply put. So they use the default StockJayS throughput estimator. It's not very accurate. As a result, their algorithm was being supervised on bad assumptions. And I talked to the authors quite a bit about this, and they're aware of it. But I don't believe that these flaws are insurmountable. And for example, something simple like a sideband throughput estimator, which is where you just download a little bit of the last segment at line speed to more accurately measure throughput, seems like a good match because L2A is only concerned about the throughput of the last segment in the first place. So, and of course, as we've seen from Stallion, there are simple solutions to the playback rate increases causing further stalls. So LOL, the throughput estimator appears to be accurate. And I know I said appears here, it's because these are synthetic. We're not capturing the complexities of what happens in the real world, especially with TCP. But the changes that the authors made, especially when the burstability has been reduced, do appear to work. And the upswitch behavior looks especially promising. We did like the author's self-organizing map approach, but we did not like the hard-coded weights that were behind a lot of the tuning. And one of the big parts of, or one of the parts of the self-organizing maps criteria was an aggregate QoE score, where it takes in bit rate, playback rate, stall duration, and it uses that to make an aggregate single number of QoE. We thought that was really interesting, but in my experience, I initially set out to use that number to grade these submissions. I could not find weights that made me happy. And I feel like it would be really hard to find weights that would work well for the diverse Twitch network. And I did talk to the authors about this, and they recognized the problem and discussed dynamically setting the weights in the future, which would be really interesting. And just to touch upon the heuristic approach, it just switches too often to be recommended. Stallion. Like I stated before, the trade-off between bitrate and stall duration is favorable. The percentages seem large, but the actual values are pretty small. We really liked how simple and effective and to the point the ideas were. We really liked that they addressed the playback rate. StockJayS maintainers, if you're listening, you should probably implement this. I think it would make a big improvement to the low latency streaming stack you have set up. But we also didn't feel like Stallion made significant improvements to the default -JS algorithm, because one of the big problems is upswitch behavior, and removing the jitters from using a standard deviation isn't necessarily going to make the throughput estimator switch up better, just because the measurement itself is still lowballing. So, drum roll please. L2A LL wins first. Congratulations to the unified streaming team. LOL in second and Stallion in third. We really liked L2A. We really like the attention to detail and the rigor behind it. And we think it has a lot of potential, and especially convex optimization, we feel was a better choice than self-organizing maps. And that's what put them ahead. But this was a really hard decision. It took me honestly like weeks to figure this out and to look at the problem from every angle, and it was not easy to pick a winner. So everybody should be really proud of themselves for making it this far and submitting a paper. And that's all we have time for. Well, that's all I have to say. I think we have some more time for questions. Thanks, everyone.
All right. Thanks, John. Thank you very much. So I believe we have a couple of questions, although we don't have much time, but let's see. Okay. You can probably see them on screen, John?
Yeah. Okay. So
yeah, you can just go ahead, read Christian's question and then answer it.
Yeah. Okay. So a question about when low latency matters. Yeah. So it does require a lot of investment, and it isn't, not everybody needs low latency. I'm the biggest proponent of low latency. I'll be the first to say that. Not necessary for live, of course. Live sports, you could honestly, like, it's a matter of opinion. I believe it's important for live sports, especially when you're potentially near people who are watching the game on TV, which has lower latency, and they cheer about the results before you see it. So I think it is a big issue for interactive streaming, for feeling connected to an audience if you want that kind of experience, but it isn't necessary for all use cases, and it is pretty expensive.
Yeah. All right. And then I hit to ask this question. So
can we count on it? Yeah, no, but honestly, I would like to do more. I think it's really interesting. I just think that this year is going to be a big year for low latency streaming maybe a bit dulled by COVID. I'm expecting to see a lot more into Mux, but I'm really curious where the industry starts heading. I feel like at some point we're kind of hitting the potential for HLS as it's written, for Dash as it's written, and for client side adaptation as it's been implemented. So I'm really interested to see if the industry starts going to bespoke streaming or bespoke streaming methods just to get around latency, where WebRTC is going, and what is the role for a server to start informing the client of changes or of network, giving hints, maybe not deciding what the quality should be, but helping the client make that choice. So I would be really interested in seeing more academic research focused on those areas. Like what can the server do to tell the client how to better switch? So if you could think of stuff like that, sure. It's hard to commit right now. It's a large time investment. And we want to make sure that if we do submit another challenge, that we're really doing something that calls focus to an area which has a lot of potential.
Yeah, certainly. But I hope that this was a rewarding experience for you guys.
Of course.
At least, you obviously spent a lot of time, but hopefully it was well spent time for you.
No, yeah, of course. We're so happy to get the 3 submissions, and they're all really interesting. And I would love to be able to take these ideas and put them on the Twitch network, which is something we're talking about, and to actually conduct tests at scale and see how these ideas shape up. And I'm especially excited to see the 2 machine learning approaches, because I think that is an idea. Those are ideas which have yet to be explored by the industry, like by the engineering teams and companies. And they do appear to have a lot of potential. I will say they're pretty hard to understand for the average engineer who's not familiar with machine learning, but there's so many resources out now that it's not insurmountable. And that's one of the reasons we liked L2A quite a bit, is because they thought about performance guarantees in the context of streaming. And that is especially appealing to a company like Twitch, where we could say, well, the algorithm isn't going to go sideways and we won't know why, and we'll have to debug a black box. It's like, well, mathematically, it'll probably hit this average, which is a really cool thing to prove in the paper.
Indeed. All right. Thank you very much, John, again.
Yep.
And thanks for the effort and the support for this year's MMSys. And looking forward to next year. Thank you.
Yeah, thanks again, Ali. And I just want to say thanks again to you and your team, especially for helping us through the way, and especially with some of the code and setup and the evaluation framework.
Thank you.